Hello there, students of chemistry. This is a recording about how to do equilibrium calculations. This goes with your notes that say calculations involving equilibrium constants. I'm not going to do all 9 of these example problems because, for example, 2, 3, 2 and 3 are the same. Number 4 is only different because it's a base instead of an acid. And number 5 and 6 are the same. But we're going to look at a few of these together. I would encourage you to complete the others in your notes and check your work. So this first example problem is about as easy as equilibrium gets. This is as hard as it's going to get on your final exam for the state of North Carolina. But you can see that as we read the problem, they give you the equation. Phosphorus pentachloride in the forward direction yields phosphorus trichloride and chlorine gas. And they give you a temperature because remember that an equilibrium constant is specific to a temperature. And then it says the equilibrium concentrations are 1.27 molar, 2.229 molar, and 0.229 molar for the chlorine gas. So when you have these problems, there's 2 things you should do. The first thing you should do is write your equilibrium constant expression. That is using the law of mass action. And in this case, I don't really care that you write this, but this is a Kc because it's a general equilibrium dealing with concentrations. The equilibrium constant is equal to the sum of the concentration of the products. The product of the concentration of the products. I said sum. Divided by the product of the concentrations of reactants raised to the power of their coefficients. This equation happens to balance with a 1, 1, and 1, so we don't have to raise anything to the powers there. So this is how we're going to calculate the value for the equilibrium constant. So when it says, what is the equilibrium constant? What is the value for it? You're solving here for K. K is what we call the equilibrium constant. So the other thing that you should do when you're faced with a problem like this is go ahead and make an ICE chart, just in case you have to do some stoichiometry. ICE stands for initial, change, and equilibrium. Before, when we were doing reactions that went to completion, we used a before, during, and after reaction chart. And in the after reaction portion, there was always something that was 0. That is not the case here for equilibrium. So what they've told us is the equilibrium concentrations are. So what we're plugging into this chart is 1.27 molar, 0.229 molar, and 0.229 molar. I know this seems redundant, but it's important for you to understand that the values that go into the equilibrium constant expression are the values in the equilibrium portion of your stoichiometry chart. Initial, change, equilibrium. And since we have those, we can just plug and chug. So Kc is equal to 0.229 molar times 0.229 molar divided by 1.27 molar. And then you can chug that out in your calculator. That's going to give you a value for K that is 0.3 significant digits, 0413. So the last question that's asked is, are reactants favored or are products favored? You learned in your recording on the equilibrium constant that if the value of K is greater than 1, we would say that products are favored. So this value is less than 1, and this equilibrium, reactants are favored. Meaning that the reverse reaction is moving as a stronger reaction than the forward reaction. So we're going to get very few products. Most of the reactants are going to stay reactants. Example problem number 2. We're dealing with a weak acid, nitrous acid. We know that acids are going to react according to the equation HA plus water yields the conjugate A minus plus hydronium. Acids make hydronium whether they're weak or strong. This is a weak acid, so this is in equilibrium. You are told that the acid dissociation constant is 4.5 times 10 to the negative 4. So the two things you should always do when you approach these problems is go ahead and make an ICE chart, do your stoichiometry chart, ICE, and write your equilibrium constant expression. Ka equals the concentration of A minus, because that is aqueous, times the concentration of hydronium, because that is aqueous. We're going to leave out the water because water is a pure liquid. Pure substances, i.e. solids or liquids, have constant concentration, so they are not going to alter the equilibrium position. So on the bottom, because our acid is also aqueous, that concentration will be on the bottom. We've got 1-to-1 ratios. That's kind of the nice thing about all of these, is that they are 1-to-1. And it says we have a solution that is 0.002 molar nitrous acid. That is the initial concentration of the acid, 0.002 molar. Now, typically when we do stoichiometry, we have to put moles in the chart, but here we can use molarity because the law of mass action requires molarity. So we know that in the beginning we have zeros here. We don't know what the equilibrium concentrations are going to be. So what we're going to do is go, okay, I know the amount of the acid is going to go down, and it's going to go down by this amount x. So at equilibrium, we have 0.002 minus x. Now, I know that according to the stoichiometry, if that goes down by x, this goes up by x times the mole ratio, 1/1. And this goes up by x times the mole ratio, 1/1. So at equilibrium, the concentration of A minus, in this case that would be the nitrite ion, is x. And for our hydronium will also be x. This problem is asking us for pH. So we know what we need is the equilibrium concentration of hydronium. Remember, those brackets mean concentration of, and that will allow us to calculate pH. So we just are going to plug these values into our equilibrium constant expression, and what you end up with is something that looks like you might have to use the quadratic equation, which is not a bad thing. If you are someone who likes to graph the quadratic equation, you can do that. But there is a little trick that we use when the value for the equilibrium constant is small. What we do is we're like, okay, this value of x is going to be so small that it is not going to change the 0.002 significantly. So we say that that concentration x approaches 0 and we ignore it. And that usually works. I'm going to tell you, for us, it will always work in this class. So Ka is equal to the concentration of A minus, which is x, times the concentration of hydronium, which is x, over the concentration of the acid, 0.002. We were told that the value for Ka is 4.5 times 10 to the negative 4. So you're going to solve algebraically for the value of x. X is defined as the equilibrium concentration of hydronium. So once we have that, we can solve for pH. So algebraically solve for x, 4.5 exponent negative 4 times 0.002, that's going to equal x squared. So the square root of that number will give us our answer, 9.4. One significant digit. That's not nice. 9 times 10 to the negative 4. And because it's a concentration, we'll plunk that molarity on there. Okay, so now that we have the concentration of hydronium, we can get pH. pH equals the opposite of the logarithm of hydronium concentration, which is 9 times 10 to the negative 4. To one significant digit, we use one decimal place on the pH. The pH is 3.0. And you would follow through on number 2 the exact same way. You have acetic acid. You can write the formula for acetic acid, or you can always go back and use this general equation, HA equals. That's up to you. But these are always going to be interacting with water. So on the third problem, what we have is a weak base. The only thing that's going to be different about this one, this is problem 4, is that instead of making hydronium, this is going to make hydroxide. So ammonia, which is aqueous, plus water, is going to make hydroxide. Ions are always aqueous, and ammonium ion. So the only thing different here is that if you have initial change equilibrium, our equilibrium concentration is going to be of hydroxide ion. So if we're going to get pH, what we're going to have to do is get the pOH first. So pH is equal to 14 minus pOH, and we'll have to solve for the equilibrium concentration of hydroxide, which will be our X. So you should start every one of these problems by making an ice chart. It is 0.5 molar ammonia. That goes down by X. These always start at 0. This goes up by X times the mole fraction, 1 over 1. And you should write your equilibrium constant expression. The equilibrium constant expression is what we get from the law of mass action. So Kb equals the concentration of hydroxide times the concentration of ammonium divided by the concentration of ammonia. All three of those things are aqueous. And then you can plug and chug into your expression with the equilibrium concentrations. Remember that for us, we're going to always say that this change in X approaches 0, and we're going to ignore it. So Kb equals X times X over 0.5. We know that in the problem they told us what the Kb is, and that is 1.8 times 10 to the negative 5. And then we can solve algebraically for the value of X. X is defined as the concentration of hydroxide at equilibrium. Just put that EQ at the bottom. So you get a hydroxide concentration of 0.003. If we want to know the pH, pH is equal to 14 minus pOH, and the pOH is the opposite of the logarithm of 0.003. pH is 11.4, 11.5. And you should always ask yourself, does the pH make sense? What we have is a base, we should get a basic pH. And 0.5 is pretty concentrated, so you might be going, but if it's a weak base, why is the pH so high? I would think that weak bases are closer to 7. And I think the thing that you need to remember is that pH is about concentration, not about strength. So if you have a more concentrated, you can have a really concentrated weak base, and it's going to have a very, very high pH. Okay, so the next problem, the ethylamine. If you want to make the equation for that one, and if you don't know what ethylamine is, and I don't expect you to, they tell you it's a base. So you can just use the general format, B plus water. Bases are always aqueous. That's going to yield HB, that's the conjugate acid of the base, plus hydroxide. So you can follow through similarly with that one. So the last example, the last type of problem we have, we're going to skip down here to number 7, which is a KSP problem. What is the concentration of iodide in lead 2 iodide in a saturated solution? So a saturated solution means we have all the ions that we're going to get. So the first thing we should do is write our equation. Lead 2 iodide is a solid. A saturated solution means that it has dissociated into its maximum number of ions. Our solid has dissociated into its maximum number of ions. So if we make an ice chart, it's going to look like that. Let's go ahead and write our law of mass action. Our equilibrium constant, KSP, that is called the solubility product constant, is equal to the concentration of lead ion times the concentration of iodide squared. We do not include the lead 2 iodide because it is a solid. Solids and pure liquids do not participate in equilibrium, but ions are always aqueous. So we will always include ions. So here's the thing, we know that these start at 0. We don't know how they're going to change. But if we say, okay, the lead is going to change by X, it's going to go up by some amount X, that means that using the stoichiometric ratio, iodide is going to go up by X times 2 over 1. So at equilibrium, we have the concentration of lead ion is X, the concentration of iodide ion is 2X. We can plug that into our equilibrium constant expression. KSP was given in the problem, 2.4 times 10 to the negative 4, equals the concentration of lead ion, X, times the concentration of iodide ion squared. So that's going to be 2X squared. If we solve algebraically, 2.4 times 10 to the negative 4 is equal to 4x cubed. So if you don't remember the algebra of how to get there, you have to square the 2. So 2 squared is 4, x squared is x squared. 4x squared times x is 4x cubed. And then we just solve for x. X is equal to the cubed root of 2.4 times 10 to the negative 4 divided by 4. Remember that the cubed root button is under math, and it's number 4. And our value for X is the concentration of lead ion, and that is 0.039 molar. Now the problem didn't ask us for the concentration of lead, it asked us for the equilibrium concentration of iodide. But if we know that the concentration of lead is 0.0039, then we know that the concentration of iodide is twice that number because of our 2x here. So the concentration of iodide is 0.078 molar. So this is how we handle solubility product equilibrium. You had an acid, you had a general equilibrium problem, right, the first one, and then you had an acid equilibrium problem, and a base equilibrium problem, and then a solubility product. I want to go back and do just one more. So on your notes, this is number 6, and it's asking you to, let's not do number 6. That one's easier than number 5. Let's do number 6. Okay, nope, we got to do number 6. Okay, so here's the thing with number 6. It's asking you to solve for the Ka of the weak acid. Formic acid is an organic acid. The acetic hydrogen is in the back. I don't care that you use the formate ion. You can use the general equation, HX, or HA, plus water, yields A minus, plus hydronium. So here's the thing. It says that you have, in your ice chart, you start with 0.025 molar formic acid. Zero's here, and they're telling you that the concentration of hydronium is 2.03 times 10 to the negative 3. So at equilibrium, we know that we have 2.03 times 10 to the negative 3rd here, which means this went up by 2.03 times 10 to the negative 3rd, and this went up by the same 2.03 times 10 to the negative 3rd times the mole ratio, and it is 1/1. And then the formic acid went down by the same amount, 2.03 times 10 to the negative 3rd times the mole fraction, 1/1. So at equilibrium, we have 2.03 times 10 to the negative 3rd molar of the conjugate, and then 0.025 minus 2.03 times 10 to the negative 3rd is to 2 significant digits, 0.023. Write your equilibrium constant expression. Ka equals the concentration of the conjugate times concentration of hydronium divided by the concentration of HA, the acid. Remember, if you don't remember the definitions of conjugates, you might want to go back in the last unit and look at those. And now that we have equilibrium concentrations, we can plug them into our equilibrium constant expression. So Ka equals the concentration of A minus, which is 2.03 times 10 to the negative 3rd, times the concentration of hydronium, 2.03 times 10 to the negative 3rd, divided by the concentration of the acid, 0.023 molar. And then if you just chug that out in your calculator, Ka for this acid is 1.79 times 10 to the negative 4. One of the things I probably should have changed about this is that most of the time when you're solving for the equilibrium constant, the acid dissociation constant for an acid, they don't actually tell you what the hydronium ion concentration is. They'll tell you that by giving you pH. So a better example of this would be if they said, instead of giving you this, they would say the pH is equal to 2.69. And then from that, you would have to calculate the hydronium ion concentration. So you would say, okay, hydronium concentration from the pH is 10 raised to the negative 2.69. And that's how you would get the value that you were putting here in your ice chart from this setup here. So it's much more common that instead of just being given the number, that you're given pH. Remember that you can get hydronium ion concentration from pH by raising 10 to the negative pH. Okay, so this is how to calculate equilibrium concentrations. Before you start in on your problem set, I would like you to answer the questions that we didn't do, and then have those checked, and then you can get working on your problem set dealing with equilibrium concentrations.